Vice Chancellor is here, Professor Dr. Bushra Mirza. The Vice Chancellor, Lahore College for Women University, LCWU, is dynamic lady, an illustrious scientist, and very good teacher. She did her PhD from the Cambridge University, UK, in 1996, and postdoc from the University of North Carolina, USA. Her area of expertise is molecular genetics of medicinal plant. She has been awarded the prestigious Tamgha-e-Imtiaz Presidential Award in 2017, Best Research Paper Award 2009, and PAS Gold Medal Award 2008, A.R. Shakuri Gold Medal in 2010, and much more. Academic Excellence Award in 2022 by the Private Sector Association of Pakistan. She has produced more than 100 MPhils and 20 PhDs. She has more than 150 peer-reviewed journal publications with an impact factor of 200 and 1,000 plus citation. Please, Professor Dr. Bushra Mirza, share your words with us.
Bismillahirrahmanirrahim. Thank you very much for kind introduction. I welcome you all to the international webinar on material sciences in current era. And I must congratulate Dr. Zohra Kiani, the physics department, and her team for organizing this webinar. I see that they are doing such activities quite actively in recent past. And again, this webinar is definitely one very good addition in the list of activities which they have been carrying out, particularly because I see that, this topic of material sciences, which is sort of a bridge between physics and many other fields, including chemistry, nano technology, biotechnology, engineering, and so on. So, this topic is very interesting, and I'm sure the scientists she has gathered are best in their field. I see a galaxy of experts joining from USA, UK, China, Germany, and within Pakistan. Of course, several brilliant minds are going to be part of this event. So I'm sure they will be talking about the latest advancements in the field of material sciences, with emphasis on all of its aspects. So I'm sure it would be a wonderful opportunity for our young researchers, faculty members, as well as students to learn from these experts and to see the future possibility of future collaboration. So I wish you all the best. And I hope that this activity will be very productive and will lead to several collaborative initiatives by our faculty of particularly physics department, as well as other relevant departments for better research environment of our university. Thank you very much.
So nice of you, Professor Dr. Bushra Mirza, and thank you for nice words. And now we may switch to our session with the first talk by our respectable Professor Dr. Riaz Ahmed with the title of Deposition of Oxide Thin Films Using Plasma System. Over to you, sir.
Thank you. Thank you very much. And sorry that I could not find you earlier due to some problems.
No, sir, it's okay.
Okay, so today I'm going to talk about the deposition of oxide thin films using plasma system. So I start from the very basic thing, which says that ionization. So ionization, basically you give energy to the electrons and it leaves the atom and atom becomes ionized. So this is the basic part of the plasma, this ionized gas. And there are three processes occurring in the plasma: absorption, spontaneous emission, and stimulated emission. So these are basically occur in plasma. And when we define plasma, so plasma can be defined as an ionized gas, but not necessarily ionized gas is a plasma. So ionized gas should have two kinds of properties. Number one is the collective behavior, and the other one is the quasi-neutrality. So quasi-neutrality and collective behavior, if any gas has these two properties, you can call it plasma. So plasma is not a neutral, but is a quasi-neutral system. So we have in plasma, we have long range forces, we have short range forces. Long range forces is basically responsible for the collective behavior, which is the Coulomb's law. And that is the very basic part of the system. The other one, which is the short range forces, they are fusing, when two atoms or molecules, they fuse together. So they actually, it can be used for that. And that is repulsive and attractive forces occurs. And this is the part, this formula is given here. And this is the potential curve which occurs when you close together. Once it is repulsive, if you have the same charges, and then it got the attractive behavior, which is if you becomes much more closer. So in plasma, it basically occurs in the universe everywhere. For example, lightning. Lightning occurs in the sky, and you see the lightning. And the neon and fluorescent lights and the water experiments, they occur in the labs and in the on Earth. And the astrophysical plasma, you have no limit. Solar winds, Earth magnetic field to compress this, creating a shock wave called bow waves. When this is the bow waves, which is any stars and stellar mediums, they are all plasma. And you can observe plasma by looking at this their colors coming from the system. So why we are interested in plasma? The first and foremost thing is the fusion energy, which is the potential and the safe energy, and it is abundant on Earth. The other one is the astrophysical plasma, which is whenever you go out of the Earth's atmosphere, you actually you interact with the plasma. So understanding of plasma helps us to understand stars and stellar evolution, and which is the important part of the astrophysical systems. The upper atmospheric dynamics from the Earth. The upper atmosphere is plasma, so it is used in the communication systems. So we can say that this is also important. And the other plasma applications which we employ here in the lab, plasma can be used to build computer chips and clean the toxic waste. And I'm giving two diverse applications. So applications are plenty of applications, So we work on the nonlinear plasma, which is used in the non-equilibrium plasma used in the processing of the materials. And it is in plasma, we can use chemical synthesis, plasma spraying, diamond film deposition, and ceramic powder. You can make plasma out of that, and then you can deposit on the systems. The light sources, high intensity discharge lamps, low pressure lamps, they are being used in the world now, and the special kinds of sources of light as well. The surface treatment, ion implantation, hardening of the material, welding, cutting, drilling. The plasma used in a variety of the applications. And space propulsion, which is when you fire your rocket, so it is used to serve as an indhan. The other one is space flat panel display, which is they are working on these systems. Switches, electric power, pulse power energy system. So it can act as a switching of high power switching energy, and the converters, magneto-hydrodynamic converters, thermodynamic energy converters, surface treatments, instrument sterilization, and lasers, free electron lasers, X-ray lasers, and all kinds of gas lasers. They contains plasmas. So high power radio frequency sources, material analysis even. With the X-ray, you can analyze the material. And the microelectronics devices, there are plenty of work going on in the world. that fluorescent lights, television, displays, and it actually estimated to $200 billion business. And $250 billion business is a semiconductor energy device, semiconductor industry, where it is used in different kind of setup. So in the absence of it normally says that is a $2 trillion telecommunication industry exists. So the plasma technologies is serving them. The biocompatibility of the implant, surgical implants, sterilization, and plasma-aided surgery devices. So for the plasma can be divided into two main groups. Number one is the high temperature plasma, and the other one is low temperature plasma. But it is further divided into high temperature plasma means temperature of electrons and ions should be almost equal, or the density of the electrons is greater than equal to 10 to the power 20 per cubic meter. And low temperature plasma means the temperature is almost equal, though its temperature is about 2 into 10 to the power 4 Kelvin. And the non-thermal plasma, which we are using for the plasma processing of materials, that is the non-equilibrium plasma. So it has temperature around 300 Kelvin to 1000 Kelvin. And here we have temperature of the electron is much, much smaller than the ion temperature. And the density of the electron is much smaller, which is 10 to the power 10 per cubic meter. And the fusion is that when we use deuterium and tritium, we can heat them to 150 million degree. So we receive neutrons and the helium. And so neutron is basically, they are carrying the energy. And presently fusion is important because ITER program in France is a 35-nation collaboration. They are trying to design, they are designing it $20 billion budget, with $20 billion budget. So it's a huge project. And they think that they will be making a reactor for the energy. So fusion energy all over the world is used in USA. So consumption, because consumption is all over the world is increasing. For example, China used energy 120 gigawatt energy, but now they are using 500 gigawatt energy. In 10 years, in 30 years time, they increased almost 4 times. And even India is increased much, much higher than even 5 times, 6 times higher than the energy. So we need an energy source which can give us this kind of energy. So plasma can be confined. It confined in 3 different methods. There are 3 basic different methods. Magnetic confinement, which is actually using magnetohydromagnetic confinement, which is you can say stellarator or can be used and gravitational confinement, which is present in the stars and suns, and the inertial confinement using lasers. So inertial confinement, you have a laser from the 4, 5, 6 sides, and it compresses the plasma, and then can have it raise the temperature about 100 million degrees centigrade. So we can have then plasma over here, and we can use that energy for the reactor. So the work which we are doing, we are implanting or depositing material. So we can use this kind of setup. This is called plasma assisted systems. So we have plasma here, we have a substrate here. So here, this is an example that we can use silane gas for silicon dioxide, and pressure about this much. Temperature of this plasma is about 100 degrees centigrade to 800 degrees centigrade. and plasma density 10 to the power 9 per cubic centimeter, and temperature is about 5 to 10 electron volt. So here we can see that when radical coming from the plasma, they actually sitting onto the surface, and the ion coming from the plasma, they interact with the substrate, and then they become part of the substrate. And radicals, because they don't have so much energy, so they react in the plasma but not on the substrate. So they will form cross-linked, and then the film grow on the surface. The other part is this system, which is we have two kinds of, this is the substrate, and this is the plasma. This is the another electrode. The ions are accelerated into the target, and some of the surface of the atoms are sputtered off to the target, and these sputtered atoms flow across the chamber, and they were deposited onto this substrate. So this is the sputtering, basic sputtering phenomena. And the sputter system contains that we have an electrode, and this is the two electrode system, and we have a target onto the one electrode, and the other one we have substrate onto the other electrode, which is called the counter electrode. So the plasma provides ions. Ions accelerated through the electric field, and they sputtered material from the target material from here, and that transport target sputtered material towards the substrate, and during they pass through the plasma, and they have some kind of reaction with the plasma species, or they will then adsorb to the substrate and then diffuse it to the substrate, and they form the nucleation and the film form. Nucleation occur and the film form onto the substrate. If we place a magnet behind the target, this is the target. So then we confine the electron beam. So electron beam is confined due to the magnets present behind the target material. So it actually covers the distance, and it moves in a spiral path. It means it will have it now larger electron collisions. So they collide with the plasma because its path length has increased in this curving behavior under the magnetic field. So this means that they produce more ion. They produce more ions, and they will interact with the plasma, and then they go on to be diffused or adsorbed onto the substrate. So this means that with the magnetron, the density of the ions will increase. So this means that we have now the rate of deposition of film is increased greatly, and this is beneficial. So the other part is the radio frequency plasma system. So radio frequency plasma, basically we have a sinusoidal kind of power system we are applying to the electrode. So this means that now we don't have cathode and anode. So it means in one cycle, one electrode becomes cathode, and the other part, and in the other cycle, it becomes the cathode. So this means that the plasma now oscillate between. So, and the important part of the radio frequency plasma is that it actually deposits material even we don't have conducting electrode. So that is the most important system, and so it can deposit material without considering the uh, metallic electrode or even insulating substrate or material or the electrode. The other system which we had in our, so we had a radio frequency system, a magnetron system, we have DC magnetron system here. We have two kinds of system present in our lab, and the dense plasma focus is another part which is present, and we are using that system for depositing the deposition of the material. Since it is high temperature, high density plasma, so we use that dense plasma focus for to deposit a material. It can deposit any sort of material you can name. So we have different kinds of biomedical applications I already explained. So this is the uh, usage hip-knee processes. It's about, people are 1 million people have been using that, and with the plasma we can make surface bio-friendly. So we can deposit hard coating films, the titanium nitride, aluminum nitride, titanium carbide. So we can see that the hardness of the film is increased, so as the life of the tool has increased. Plasma display panels. So this is the plasma display panel. Here we have an electrode here. This is the address electrode. This is the protective electrode. And this is the phosphorus screen. And this is the pixel. So we can magnesium oxide layers here. And this is the display electrode, dielectric material, and the front plate glass. And this is how it actually works. The voltage creates electric field, and we have xenon and neon gas release by using this UV light, and the photon interact with the atoms, and it actually interacts with phosphorus screens, and then we can see the light onto the screen. We deposited a biomaterial film, which is the titanium oxynitride film. So you can see here we have the XRD pattern where we can see the nickel titanium, titanium oxide, and titanium nitride peaks. They are deposited at different flow rate, oxygen flow rate. So here we have simulated, we developed a simulated body fluid, which is almost like the body fluid. So nickel ion release has been checked by placing our film in the SBF, or simulated body fluid. So simulated body fluid, and then after immersion time, we have seen that after 3 days, nickel titanium alloy has 4.8%, nickel release 4.8 microgram per liter, and in sample number 1 it actually goes to 0.161 nickel. So nickel is the dangerous for the tissues. So we're trying to minimize the release of the nickel. So nickel is with the sample number 3 when flow rate has increased. So it is actually 0.092 microgram per liter. So for after 7 days, it actually goes to 0.107, and 21 days is 0.3, and even 35 days we have 0.3 microgram per liter. So we have seen that the nickel release has been decreased by using the plasma deposition after the plasma deposition of the titanium nitride. And then we have some work we did on nitriding of aluminum. Here we have seen that the hardness has increased. And this is the XRD film where we have titanium nitride film deposited. This is the peak. We have titanium nitride peak here, which is a very large. So the micro hardness has increased. So after the treatment, before treatment, it is 2 megapascal for the untreated sample, And after treated sample, it is 6,400 megapascal. So we have enhanced the hardness, micro hardness of the film. And then we have zirconium nitride. This is also an example. Zirconium film is about similar film type. The titanium has a similar property because it's a transition metal. So zirconium nitride has been deposited, and here we have increased the Vickers hardness as past 400% of the 400% micro hardness of the nitride sample, which means it is even better than the titanium nitride. Then we deposited film, think of zinc oxide thin film. And zinc, we know that zinc oxide is the most researched material, and now still people working on it, and see a lot of papers. People are working on it and publishing because of its various applications. So it can be used in the light emitting diodes, laser diodes, solar cell systems, even used as a gas sensors, even high flexible transistors, antibacterial coatings, drug delivery, and surface acoustic devices. So it has a lot of application, and so zinc is a cheaper material. So people are actually working on the zinc oxide film. So zinc oxide is a semiconductor, important semiconductor applications. So it has wide band gap, which is about 3.37 electron volt, and has a binding energy of 60 milli electron volt. So we deposited ions after deposition of the zinc oxide film. So we deposited film. We actually implanted different various kinds of metal ions, aluminum, indium, nickel. And here we have used silver, copper, and nitrogen because they act as an acceptor impurity in the zinc oxide, and it caused reduction in the band gap and resistivity of the film. So nickel and cobalt was useful to obtain dilute magnetic semiconductors. So I'm giving only one example, which is the copper doping. Copper doping is the important because various people have worked on the copper doping of the film. The zinc oxide, band gap of the zinc oxide was increased with the increase of the copper plus concentrations. So this is the paper published by Saidani et al. And the other people, they observed that the copper's dope zinc oxide exhibits strong potential in the field. And then Shukla et al. Published, they have worked on the sensing property of the copper doped zinc oxide crystal, and they found that the transmittance of the films after doping increased significantly, and whereas the optical band gap of the zinc oxide reducing from 3.28 to 3.18. So we deposited film under the argon oxygen environment, and then we implanted using the accelerator, Pelletron accelerator, for 4 different doses, and this is the setup. And we actually implanted zinc oxide onto the PET surface, which is the flexible film. So we deposited material on the flexible film, and then implanted copper ions onto the substrate. And then we checked if that whether we have found the photodetectors. So we developed this is the copper doped zinc oxide film, and here we have some connection onto the film. So under the light, we observed that the current has increased if we increase the voltage like this, and if we don't have the light, then it has smaller current flowing Then we check the responsivity of the film, which is the photo detector. This is the I into E. I is the photocurrent, and divided by E is the light irradiance, which is the UV light, and A is the activation area. And the responsivity of the fabricated nickel, and nickel is the metal film deposited onto the film for the connection. So contact. So nickel, zinc, copper oxide, nickel photodetectors at 7 volt, we have 921 milliampere per watt, which is very good compared to other results. And we have checked the quantum efficiency as well by using this formula, which is 1.24 R over lambda. Lambda is the wavelength of the UV light, which is, so value of the quantum efficiency at 7 volt is 219%, which is again very significant. And then we check the response time. And UV light is not present, so the current is 6 microampere. And when we turn on the light, then suddenly current has increased. And this is the response time from. So we can see that the response time is at 1 volt is 1.71 second, and at 7 volt is 0.52 second. So recovery time means that when we turned off the lamp or UV light, so this actually gives us the drop of the current, and this drop of the current varies with the voltage. At 1 volt is 4.19 second recovery time, and at 7 volt, 0.99 second recovery time. So this is the basic parameters which we have already explained, that this is the gain and response time and the recovery time. You can see the recovery time at 7 volt. The gain has increased to 2.1, and this is the 0.5 volt response time and recovery time. So we have compared our result with the other worker, and this is the our work. The photocurrent is 115 microampere, and we check that with the UV light. And whereas this is the people have worked on, which is for 1800, but its responsibility is decreased, but they have used biasing voltage at 10, but their response time is small, larger than ours, and their even recovery time is larger than ours. So this is the work people have worked on it. So this is the, I think, last slide of my work. If you have any questions, kindly ask questions.
Thank you, sir, for such a nice and informative talk about plasma and beautifully related with the material sciences. Now, room is open for questions. No question? Okay, I think everyone can understand it very well. Thank you, sir. Thank you again.
Thank you for inviting me.
Now we move to our next keynote speaker, Dr. Muhammad Shehbaz Anwar, from the Department of Material Science and Metallurgy, University of Cambridge, UK. He is a well-known researcher with a lot of publications in peer-reviewed journals with 900 plus citations. His field of interest are quantum materials, oxide heterostructure, superconducting spintronic, quantum phase slips, and topotronics. Please, sir. His title of talk will be Dissipation of Less Diode Effect.
So thank you very much for a nice introduction, and good morning, Assalamu alaikum. So let me share my talk. Just 1 second, please. Okay, so first of all, thank you very much to invite in this wonderful webinar. And I am also very glad to be the part of these webinars. Those are improving, are also appreciating the women in science, particularly in Pakistan. This is really the future of our science and technology in Pakistan. So my today's talk is related to dissipationless diode effect, and I hope that it will be very easy to understand because everyone knows about diodes, that how they work. Then I will show you that how we can make them dissipationless, meaning that they may not actually emit the heat energy. So then we can do energy efficient electronics. Before going in my talk, I would like to say my thanks to my collaborators from Kyoto University, Japan, and Seoul National University, and then of course from the Cambridge, and also the traditions from Zurich and Germany and Italy. So then we know that we are in a modern age are adding too much data, and that data is going to the data centers. The data centers, there are two big issues right now, those we are facing. Number one is that we are using more than 50% of the energy of the data centers just for keeping these data centers cool. And second is that the energy which is being used for the processing, the information for reading, writing, storing, and that energy is actually also, you could say, because these devices are dissipative devices, because they are working with a semiconductor technology and resistive systems. So then we are dissipating a lot of heat energy. And this heat energy is in fact contributing in carbon emission. So then converting our planet to like the red planet, the Mars. So right now we are already very close to have 1 million big data centers. Of course, there are many, those are small. And at the end of this year, we will reach this number. So it means that this is really a very serious problem. And now the big industry, for example, the IBM, Google, D-Wave, they are too much concerned about having the technology which actually would not, which would not dissipate the energy. And for this, what actually we can see that here, for an example, this is this IR camera photo of a processor. And here you can see that it is around about at 47 degrees centigrade. So this 47 degrees centigrade, it is also very bad for the device because it will also reduce the life of the device. Then you can say, okay, it's an easy thing. We can keep them cool. So we can use some cooling system. When we will be using the cooling system, then what we are doing, we are taking the heat and we are emitting that heat to the environment. And this is actually the problem because it is actually contributing in the carbon emission. So then there could be another solution, and the other solution can be that if we use the materials, those are zero resistance materials, such as the superconductors. But if we use the superconductors, then it means we will actually work at the low temperature. And then the major question is that how we can use the superconductors. Based on this idea, very recently, IBM started a very big project to develop a superconducting computer. And right now, Amazon and Google, they have also actually started the superconducting computing, including the superconducting quantum computing. And right now, the quantum computers, those we have, they also work at a very low temperature, and they are also utilizing the concepts of superconductivity, but the temperature is still pretty low. And then the components, those we need to process this, you could say, the information, we need mainly a transistor and a diode. And these two major devices, they can actually perform, you can say, the switching, and then you can actually develop the bits, and you can develop the gates, and you can do all the gate operations using these two main devices. So my focus right now here on diode and how diode works. We know that it actually allow only one directional flow of current. That, for example, here we can see that if we connect this diode in this way, that here is the positive side, it's the negative side, and then you can very easily cross this barrier. But if you will be actually moving the other direction, then you will actually face a strong and a sharp barrier, so you cannot cross it. So then this flow is only one directional. So you can say that in terms of the bit, we are 1 here and we are 0 here. And let's have a look at its IV characteristics. In the IV characteristics, you see that for the forward biasing, if we have the voltage more than 0.7 volts, it is actually based on you can say the semiconductors, the silicon technology, then you can flow the current through this device. But if you would have the negative voltage, there is no flow of current, almost nothing. So then you can switch between some resistance value to a huge resistance value. And in this way, we can perform the switching. What the problem here is that this system is the resistive system. And resistive system means that it will be dissipating the heat energy. And then now, how we can actually convert the superconductors in the diodes. Let's have a look on the characteristics. What characteristics? The current and voltage characteristics. For example, here we have a superconductor. We have connected to the battery and measuring the current and the voltage. And then the superconductor will show you this kind of behavior. And here, this central branch that we call it the zero voltage branch, that means that here our resistance is completely zero until we reach the critical current. And at the critical current, what happens? The superconductor switches to the normal behavior in the resistive behavior. So now we have the ohmic behavior over here if our current is larger than the critical current. And in this way, you can see that there is a positive critical current and a negative critical current. And a superconductor, it works in a symmetric way. That means our positive critical current and the negative critical current will be same, is equal to each other. And that we can call that this is the reciprocal behavior. But if somehow that our superconductor behaving in such a way that its critical current for positive direction and negative direction, these are not equal to each other, then it means that our current voltage characteristics are non-reciprocal, meaning that for the positive current, it is different than the negative current. Now, here you see that if, for an example, we try to make a switch out of it and we apply some current, and this applied current is somewhere here, then what we will have a zero resistance because our actually superconductor is in a superconducting state and it is in a zero resistance branch. So then now if I keep the current constant, but I only change its polarity, then it will be somewhere here. This means that now we are in normal state. The normal state means that now we have some resistance, it is not zero. So in this way, what we can do, we can actually establish a switch. And here you can also understand one more thing, that for an example, when I have a positive applied current, the system is in superconducting state. That means there is the flow of supercurrent. And the supercurrent means that the electrons, they correlate with each other and they actually, you can say, move in the form of Cooper pairs. When you will actually switch it to the negative current, now it is not anymore in the superconducting state, and electrons have lost their correlation, and now they are actually working as a normal fermions, a single electron, and in that way you are in the superconducting state, you are in the resistive state. So it means that this is also such like a diode, that in one direction you have a supercurrent and in the other direction you have a normal current. So this is the very simple and a straightforward concept of a superconducting diode. And very recently, 2 years ago, in Kyoto University, Professor Ono, he established this actually the device. Practically, what they did, they prepared a superstructure, and in this superstructure, they used tantalum, niobium, and vanadium. And these three are individually superconductors. But if you will grow just 1 nanometer thick of any of these three materials, then it will not be superconductor because it is too thin. What if you grow at the top of each other, then it means that now you are increasing the thickness, and then this actually the superlattice, it would work as a superconductor. And here what they did, they used the 40 layers. The 40 layers means that the total thickness was 120 nanometer. And another very important point here is that you can see that we have these three layers, and these three layers, they are not symmetric, meaning that they are like A, B, C structure, and then after the niobium, it is not actually after the, you can say, for example, let's consider that I have niobium here, then I have a vanadium, and next it should be niobium, then it will be a symmetric structure, but it is non-symmetric structure. What does it mean? It means that now the invergence symmetry in this structure is broken. And with the invergence symmetry, we can have spin-orbit coupling. And this system, they measured the resistance versus temperature. It was showing the zero resistance state, so very sharp superconducting state here, closer to the 4 Kelvin. So it means the system is in the superconducting state. And then they measures its resistance value with a different polarity of the current. And for example, this red one with the positive current, which is a 6.6 milliampere, and when they go to the negative current, which is the blue, then you can see you can switch between zero resistance to the high resistance. And another very interesting thing that they observed is that the effect of the applied magnetic field. And in case of, for example, we keep our resistance at a zero resistance value with the positive current, and we don't change the polarity of the current, we only change the direction of the applied magnetic field, which was in plane but perpendicular to the flow of current. And now here, with the zero resistance state, our magnetic field is positive. For example, it is upward. And then if we switch it to downwards, then this actually the device, it switched to the normal state. So what does it mean? It means that we can switch the resistance of this structure by changing the polarity of the current or by changing the direction of a magnetic field. So it means the two parameters, magnetic field and current, can be used as the switching parameters here. But then the question is that how, where actually this effect come from? Here we can try with the very simple equation. This is the resistance equation. And this resistance is as a function of applied magnetic field. Then you can call it that this is the magnetoresistance. And this magnetoresistance has a three terms. The first one, it is just the residual resistance, which is independent to the magnetic field. It does not change by applied magnetic field. But the second term, which has a beta term, and this beta is the normal magnetoresistance coefficient, which depends on the B square. So when you apply the magnetic field, of course, the resistance of the system would change, and this is the normal behavior. But the last term here, it has three parameters, gamma, B, and I. B is the magnetic field, I is the current. And gamma, this function, it remains constant. But here, magnetic field and current, you can see if you will change the sign of the B or you change the sign of the current, then you will have here the change in the sign of this last third term, and which would give you the anisotropic behavior, meaning the resistance would change, and that we call it the chiral magnetoresistance. What this gamma and beta are, B are doing here, the applied magnetic field, when you apply the magnetic field, it means that you are inducing some kind of magnetism in your material. And that means that time reverses symmetry is broken, meaning that your order parameter now is antisymmetric as a function of, you can say, the time. So then in that case, your time reverses symmetry is broken there. But this gamma function, as I already explained you in the last structure, that there they attentionally, you can say, developed an, you can say, the asymmetric structure where the invergent symmetry is broken. And in that case, we would have the spin orbit coupling, and this gamma function, this gamma coefficient in principle, it depends on the spin orbit coupling. So if you do have these two broken symmetries, number one, the invergent symmetry, and the number two, the time reverses symmetry, the both must be broken. Then you would have this chiral magnetoresistance. Okay, then in the normal metals, we know that in the normal metal, our parameter is the Fermi energy. And Fermi energy is very high compared to spin orbit coupling. So this chiral magnetoresistance effect will not be that strong there because your spin orbit coupling is not really efficient there. But in case of the superconductors, the energy term is the superconducting gap energy, and that energy is in the order of milli-electron volts instead of volts like the Fermi energy. So now in a superconductor, our spin orbit coupling have to compete with this gap energy, which is not very high. So then it means that this effect of the spin orbit coupling must be very strong in superconductors. And in this way, we can very easily get this non-reciprocal transport. And interestingly, there is a type of superconductivity that we call it non-centrosymmetric superconductor. By the name, you can understand that the non-centrosymmetric means that the crystal has, you could say, the broken invergent symmetry. So it means that those superconductors intrinsically has very high spin orbit coupling. So this upper structure which I showed you here, this is also the type of non-centrosymmetric superconductivity. However, these old superconductors, though they used to develop this superstructure, they are normal centrosymmetric superconductivity. However, conductors. So then very recently, just a few months ago, from the Delft University, they developed a superconducting device that you can call it a Josephson junction using the 2D materials. And they used niobium diselenide and niobium bromine. So this niobium 3 bromine 8, it is a magnetic material. It can also work as a ferromagnetic material. So in this structure, when you put two different crystal structures at the top of each other, then you can see at the interface, the invergent symmetry can be broken. So then you can have some kind of spin orbit coupling at the interface, and this actually the central layer, it is, you can say it might have some kind of magnetism. But this niobium diselenide, it is a superconductor. So this is a Josephson junction. And in this Josephson junction, they actually observed their IB curves. So main supercurrent is here, which is the positive supercurrent, and here this is the negative supercurrent. And when they plot it with the absolute values, meaning that they have, you can say, folded this IB curve, then they can see that there is a clear difference between the positive current and the negative current. So it means that this is also a diode, and this diode is a Josephson diode. And the interesting point of this discovery was that in this case, they do not need any applied magnetic field, and they can actually do it without magnetic field because the inversion symmetry is broken at the interface, and this central barrier, it can have some magnetic effect, and that magnetic effect will break the time reverse symmetry. So now you might have both broken symmetries in this device. So then you can actually have this diode effect in Josephson junction. Then here I raised my question. The question was that if, for example, we develop a diode where we do not need any magnetic field, what it should work spontaneously, and spontaneously means that we select a superconductor that has a broken time reverse symmetry, and that must be its intrinsic property. There is a superconductor which is very important and very interesting since 1998. It is actually, 1994. It is surprising us. This is a strontium-2 ruthenium-4. It is a layered superconductor, meaning that its structure is a layered structure like this here. And in 1994, Professor Maino from Japan, he discovered superconductivity in this material below 1.5 Kelvin. And since then, a lot of work has already been done on this material to understand its superconductivity. Initially, people were thinking that it is a spin triplet, meaning that the Cooper pairs have spin polarization. But very recently, it was discovered that now, if you perform the NMR experiment to measure the electronic spin susceptibility, then below the superconducting state, meaning that in the superconducting state, the spin susceptibility is suppressing, meaning that you are losing the spin polarization. So it might be like a normal superconductor. But then there was the observation of the internal magnetic field in this superconductor below the superconducting transition temperature. So that means that in the superconducting state, this superconductor has a magnetism, means there is a magnetic field inside. So this magnetic field means that this is not a normal superconductor. It is an unconventional superconductor that has the internal magnetic field, meaning the time reverse symmetry is broken now, as it is broken in ferromagnets. And then by actually combining these all results and our recent research, it is established that this superconductor should be a chiral superconductor, meaning that its order parameter is continuously changing with the direction, and that breaks the time reverse symmetry. Then I selected this superconductor. This superconductor, we can grow very nice single crystals. Thin films are difficult, but the single crystals we can grow up to a very high quality. And when we grow this material, we get the single crystals in this way, that here we have the strontium-2 ruthenium-4, but there are also some bright parts. Those are the ruthenium metal. So this ruthenium metal is like embedded. These are the inclusions. And if you put any other metal at the top of this superconductor, then the electronic connection between the metal, deposited metal at the top of this single crystal is very bad. What if you grow the metal at the top of this ruthenium metal, which is the inclusion, then you can establish a very good electronic interface, because it is the interface between two metals. And then we develop the devices in this configuration, where I actually first deposited the silicon oxide just to isolate all of this single crystal, except over one single ruthenium. At the top of that, I deposited another superconductor, which is a normal superconductor, niobium. So now this is a device between a normal superconductor and a chiral superconductor, a superconductor that breaks time reverse symmetry. Now this is also a Josephson junction. And in this junction, we can observe very clearly a zero resistance state, meaning that the superconducting state that you can see in this resistance versus temperature graph. Now here, if we measure the IV curve, then you can see here as well that what is going on, that we have this superconducting IV curve. You can see this, the x-axis is the current and the y-axis is the voltage. We have a supercurrent branch, and then it is actually switching to the normal state here. This dotted line is a theoretical fit, and this theoretical fit is symmetric, meaning that for this theoretical fit, the critical current for the positive direction and negative direction must be equal to each other. But here, the experimental data shows that it is in principle not similar. The positive current, which I am showing with the negative sign, sorry. So, and then here, the negative current, the critical current, they are actually different. They are not equal. So it means that this actually, the device in this configuration is a diode. And you can see it more clearly in with the absolute values, meaning that if I fold this IV curve, then you can see, for example, here, this is a positive branch, this is the negative branch. So it's a very clear change there. And then the other interesting thing was that if we increase the temperature, meaning that we are weakening the superconductivity, we are stressing the superconductivity, we are moving toward its superconducting transition temperature, where it will actually switch back to the normal state. This effect is suppressing. And then the very clear thing, a very clear message here is that this superconductor, which is unconventional superconductor, exhibit non-reciprocal transport, that is in fact the diode. And this diode effect is stressing with the increase of the temperature. And so if it is decreasing with the temperature, then we can take this, the difference of the critical currents, that we can call it non-reciprocal component. The non-reciprocal component means that how much the difference is there between positive and negative current. And as a function of temperature, you can see if we apply the theoretical models, very recent theoretical models, because this actually, the research, it was initiated 2 years back, but this year, a lot of work has been done, not only on experimental side, but also on theoretical side. And these recent theoretical models, they actually very nicely explains our result, that it is actually, you can say, the effect coming from a superconductor because of broken time reverse symmetry. And then the quality of a diode can be estimated with its this quality factor Q. This quality factor is in fact the non-reciprocal component over the average current, average critical current in case of the superconductor. And this also actually following the theoretical models, except something happening here. However, it actually very clearly shows that the theoretical models can very nicely explains our result. So then this effect, you can see that so far whatever I showed you here about the non-reciprocity of my devices is without any applied magnetic field. But still you can try just switch over here, then you can also actually try to understand that what will happen if you will apply the magnetic field. If you apply the magnetic field, then in our devices, we observed that the critical current is not stable. It is quite much unstable. And then I switched off the magnetic field. But then my device was in this configuration. Let me explain it in a simple way. For example, there is now, we applied magnetic field, then we switched off magnetic field. There is no magnetic field. What effect of the magnetic field is still there because it was in the superconducting state. And then what was happening, that here in this first IV, you can see that the critical current for positive and negative, it's different because this is in absolute values of the voltage and current. So then I can call it that this is a forward biased diode. And then if I continue to measure its IV curves, then it switched to the standard junction, meaning that the critical currents for both directions are same, but it can also actually jump to the reverse biasing, meaning this time the negative critical current is higher than the positive critical current. And with this, actually, the configuration, my device can jump between one of these three states. But if we look carefully here, that most of the time it actually stay in the diode configuration for the forward biasing or the reverse biasing, and seldom it actually go to the standard superconducting state. And the similar effect was also actually observed that if, for example, we have a different cooling cycles. The cooling cycle means that you are in superconducting state, then you warm up your system and you go to a relatively, you could say let's say the 10 Kelvin, where it is completely out of the superconductivity. Then in also this case, that if I change the cooling cycle, in the first cooling cycle, it can be forward biased, and then any other cooling cycle, it can be standard, or it can be reverse bias. So this selection of forward biasing or the reverse biasing is just the random selection of this system. And these, if we combine these all results, we can explain in the following way that we know that what we do have, we have a ruthenium inclusion in our this strontium 2 ruthenium 4 superconductor, which is embedded there. So then we can actually establish that this situation is in this way. And here we have a normal superconductor, which is surrounded by you can say an unconventional superconductor. So it means that order parameter of both of these superconductors are actually different, non-compatible. So then some kind of frustrations will develop. And these frustrations actually develops a superconducting vortex state. The vortex state means that here you can see you are actually, the vortex state you can understand with this simple graph. And this theta along the x-axis means the direction around this ruthenium inclusion, around this normal superconductor. And the b-axis is the magnetic field. So you see that this magnetic field is going to negative, is going to, you can say, the diverge, and then here it is positive. So this is actually vortex. And this vortex line which develops there, it develops, you can say, the spontaneously. It does not need any applied magnetic field, because the vortex state mainly occurs because of the applied magnetic field. But this one is a spontaneous one because of the frustration of two different superconducting order parameters. And then it can actually pin at some pinning sites, and these pinning sites could be some kind of defect there. And this, if you do not apply any magnetic field, then it will be just a simple state there. And the pinning potential of this, you can say the vortex, it can be symmetric. If it is symmetric, then your applied current, it would not change it. It will not move it in either direction, because on both directions, there is a very large potential that it have to cross. But if somehow toward the positive direction, the pinning potential has perturbed, so then in that case, our applied current will apply the Lorentz force on this vortex and it will move it towards one particular direction. And if, for example, the perturbation in this pinning potential is other way around, then your Lorentz force will also be other way around for the other direction of the current. So it means that what you can do, you can explain your actually this diode effect that it can be forward biased, it can be reverse biased, or it can be just simply a standard junction, which totally depends on the pinning potential configuration of your spontaneous vortex state. And this vortex state can actually change if you apply the magnetic field. So then it will be distorted. And then it will be actually selecting any random configuration of your diode. So this is actually our very recent results. Those are under consideration in Nature Communications, and I hope they will be published soon. And here, let me summarize my work here, that we actually have observed the field-free superconducting diode effect in this unconventional superconductor strontium-2 ruthenium-4. And then this is actually, you can say, the effect is random with respect to the applied magnetic field and cooling cycle. Theoretical models are actually explaining it very well. So then now we are actually have established a technique which can also be used to test unconventional superconductors against the time reverse symmetry, which is very important parameter for superconductors. Thank you very much for your attention.
Thanks a lot, sir, for such a nice and informative talk about superconductors. Any question? Okay, we will move to our next speaker then. Thank you again, sir. Thanks a lot for your nice time. Now our next speaker is invited speaker, Dr. Iktasam Riaz from the Physics Department, UET Lahore, currently working as an associate professor in the Physics Department at University of Engineering Technology, Lahore. She received her PhD degree from the University of Manchester in Condensed Matter Physics, 2012. Her expertise in graphene, two-dimensional polymer nanocomposite, nanostructure fabrications and analysis. Title of talk today is Buckling Analysis of Graphene Reinforced Cement. Dr. Iktasam, are you there?
Yes, Assalamu alaikum.
Yes, walaikum salam.
Can you hear me?
Yes, we can hear you. Please continue.
Can you see the slide share?
Yes. The slides are there.
Okay, fine. So, Assalamu alaikum to all the faculty members. So, congratulations to the LCWU for organizing this webinar on material science. I'm here to discuss about the recent work we have done in the UET Lahore in collaboration with the Civil Department and Physics Department of UET Lahore. So the buckling analysis of the graphene reinforced cement. One of the material phenomena which we encounter is basically the buckling. Whenever we talk about the use of the material all around us, so ranging from the household applications to the automobile industry, civil infrastructure, and all of the aerospace industry is based upon the materials. So it's very important to look what is happening whenever a material fails and how we can develop new materials to provide the robust reinforcement against these failures. So basically, the buckling is a mode of failure, which we are going to deal up over there. And all the theories which tells us about material failure gives us the basic conditions which we can employ to find out the modes in which a material buckles. So there are the different failure mechanisms which basically are there whenever a material fails. So whenever a material fails, it can be either through fatigue, creep, fracture, or through buckling. So the figure shows a short column or member of a column, which under compression and compression force is applied onto it. So the arrows of the force are indicating inwards, means that the force which is applied onto that column is compressive force. So if a material is under a ductile, the material under the deformation is the ductile material, the material will bend sideways. So there is a possibility that material bends sideways. But if the material is brittle, then it will produce a crack and the material will fracture up over there. So the behavior of the material under tensile load and compressive load is very important to understand in order to find more about the buckling. So simple, a material whenever it's under a tensile load means that the stretching force is applied onto that material, then the material will undergo the elongation. So the cables, cranes, threads, ropes, all the materials which are under the tensile load behaves in that stretching mode. But all the materials which are under the compressive load, which is under the highly compressive load, for example, the pillars, the columns, they undergo the compressive load. So these figures indicates the examples of the materials which usually when we encounter in service under the tensile or under the compressive load. When the material application is in service, means that the material is in some application. For example, the bridges, all the bridges which are constantly under the load of the vehicles are under the compressive load. So it means that is very, very important to understand that the materials can withstand that compressive load that the vehicle is crossing across or not. And here is an example which is onto the tug of war rope. So that is under a elongation, tensile strength is very important in that case. So we will be going to observe the rope under the tension. So whereas in the case of the bridge, which is under compressive load, we will look the material for the compressive strength. So as we have seen that for the buckling, we need to explain that it is one of the material failure in which the material under the compressive load is there. And whenever we talk about the material failure, then the sidewise deformation or the bending of a material under the compressive load will lead to a specific kind of the failure, which is called as buckling. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling. Which are under the the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds of. Here are some practical examples in which we are very much concerned about the materials or or the columns or the members of the columns or pillars buckling are under. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling are under. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling are under. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling are under. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling are under. So the buckling basically depends upon the instability of a material, which takes place whenever the material is under the compression, which are applied onto the different kinds. So here are some practical examples in which we are very much concerned about the materials or the columns or the members of the columns or pillars buckling. Exact equivalence is made between the load of the material and the critical load. If they are exactly equal to one another, then after the removal of the force, the bending which has produced into the material will remain over there, and there will be no exceeding deformation into the material. So this is what the physical meaning of the buckling is. With the help of that examples, which we have seen that the materials under all the type of the compressive loads, and specifically those materials which are used in application in the form of the long pillars and cylinders, can undergo buckling phenomena, which is a sidewise bending or the deformation of the material. So it's very helpful to analyze the theoretical analysis of buckling. So Euler buckling analysis is one of the authenticated way to find out the critical buckling load, which can be calculated by this theorem and can be helpful for finding out the critical value at which the material will start buckling. So this formula was derived in 18th century, and according to this formula, there are certain assumptions which needs to be made when we are talking about the application of the Euler buckling analysis. So we need to consider that the column or the pillar on which we are going to apply this critical buckling analysis, it should be not deformed initially. It is in its original state. Secondly, there is no other failure mechanism, like we are not dealing with other failure mechanisms like fatigue, creep, or bend, for example, the cracks or fracture. So they are not present over there, and the cross section is uniform throughout it, and the force is applied uniformly. The material on which it is applied is isotropic or homogeneous, and it very much dependent upon the pinning conditions of the column. So the columns are pinned on both ends, or they are loose from one end and pinned from one end, pinned in the middle, pinned at the extreme ends. So all these are very important. So ends of the columns are in what status? They are very important. So according to this critical buckling formula, so the critical buckling load, which is represented by PCR, is directly related to E, which is Young modulus, I, which is a cross-sectional area, and inversely proportional to the square of the length. So according to this formula, we can be able to determine that critical load at which the buckling is going to be started up. So if you know this load, critical load, then you can find out the stress at this particular load by dividing the area of the column. So sigma, which is your critical stress corresponding to the critical load P, can be determined by dividing it by simple formula of force per unit area. So ultimately, we'll be going to having the second equation, which is representing as pi square E I over AL square, in which E is the Young modulus, I is the cross-section area of the column, L is the length of the column, and A is the area. So in order to deal with such a material failure in the form of the buckling, what kind of the materials can be suitable for it? So in order to avoid material failures, so there is a great interest these days onto the nanocomposites. So before going in details of the nanocomposites, the composites are simply defined as the materials which are having such kind of property that they're light, strong, flexible, and durable. The idea of the composites starts very, very early in the history of the mankind, when we observe that the natural structures like wood, bones are made up of two or more than two materials. For example, we talk about naturally occurring composites, and then we'll talk about man-made composites. So naturally occurring composites are all those which the mankind observes all around in nature. For example, the wood is made up of this concept of the composite. The bones are made up of this structure of a composite. So in which one material is working as a base material and the other is working as a reinforcement material, or basically a filler material. So the fibrous structure of the cellulose is working as an inclusion in a matrix of lignin in the wood structure. Whereas if you look at details of a bone structure, we'll be going to find out that collagen is present in the form of the fibrils or fibers in the protein, in a protein matrix, which is calcium phosphate for our bones. So looking into this kind of the composite structure, so mankind started to work upon manufacturing its own or fabricating its own man-made composites. So initially, the history tells us that the first construction material, which was formed in the form of, which was introduced in the form of a composite, was use of straw to enhance the strength of the mud. So whenever the simple mud was used into the construction, it was always observed that the cracks are produced into it. And in order to avoid these cracks and to give more stability to this structure, the straws were added, or the different fibers were added into the mud, or the raw material was added to the mud to provide the more strength, and then it came toward the brick structure, in which we have seen that whenever the different materials are mixed and matched together, the new properties of the composite or added materials are obtained into the composites. So now these days, the different structural composites are used, including steel reinforced composites, polymer reinforced composites, in which the materials are reinforced, like polymers are reinforced with the help of the glass fibers or carbon fibers to give the new or additional properties of material. Specifically, if inclusion or addition is made into a base material with respect to the mechanical properties, then the particular terminology used for this is called as the reinforcement. But if that addition or the inclusion of the material which is added into a base material is not with respect to the mechanical strength or in terms of the other properties, then the inclusion which is added up over there is termed as a filler. So these are interchangeable terms. Sometimes it is called as reinforcement and sometimes it's taken as a filler. But the only difference is between that property which we obtain from a composite. If it is a mechanical strength achievement, then we will call it as a reinforcement usually. And if it is in the form of some other change, for example, the temperature stability or corrosion resistance or UV protection or hydrophilic or philic property addition to the material, or a lightweight, or even we talk about reducing the cost of a material or the weight of a material, then that addition which is made is called as a filler. So what are the main ingredients when we are talking about the composites? The main constituents of the materials when we are talking about the composites are the matrix, and the second inclusion or the addition which we are doing upward is called as the reinforcement. The matrix is the phase which is basically in the bulk form, and it's basically surrounding the addition or the reinforcement. It provides a support to the other material which is added up into this matrix phase. So reinforcement contributes to the basic physical or mechanical properties, and it is added in a minute quantity to the matrix. So classification of the composites can be done on the basis of many parameters. If they are done on the basis of the matrix, which is the material, then we can talk about the polymer matrix composites, metal matrix composite, and ceramic matrix. All the known materials, if they are used polymer, metal, or ceramics as a matrix, then we call them as polymer matrix composites, metal matrix composite, or ceramic matrix composites. So as we know that for structural composites, a ceramic, cement, concrete, and such kind of the mortar or cement paste are used for structural infrastructure. That's why today we will be going to talk about the material failure, which is a particular phenomenon of buckling in the cement matrix composite, which belongs to the ceramic category of the composites. If we talk about the classification of the composites on the matrix basis, then we can classify it as polymer, metal, and matrix. But if we classify them on the basis of the addition we have made or the inclusion we have made, which we are calling as a reinforcement, then the reinforcement can be added in the following forms: fiber, particulates, structural, or viscous. All of these can be added into the composites to get the new or improved properties of the material. So if the fibers are added, then they may be continuous, they may be short, or they are combination of more than two types of the fibers. So if you're talking about the particulates, then different types of the nanoparticles or layered materials can be added into it. Structural composites are those kinds of the composites which are very famous in kind of the heterostructures or in terms of the textile industry, where we arrange the different layers of the material or the composite material on the basis of the different materials. If for example, you're talking about the textile industry, the composites are made by using the different fibers. They are oriented at different angles. So the structural composites are basically those composites which are being added which are being formed by changing from one layer to another layer. And the viscous are those kinds of the material which are the single crystals which can be added as a reinforcement. So here we are only going to focus upon the particulate as a reinforcement into this work. So ceramic matrix composites if you're talking about CMC, so these are cement matrix composites or ceramic matrix composites. They are the traditional, basically, structural materials which were used as the form of the clay or the cement. But if you're talking about the advanced ceramics, so advanced ceramics are used in terms of the carbide and nitride. Here we will be going to focus on these traditional structural materials as cement. So cement, if it's a fine binding powder, which is alone is not used for construction material. It is always used with some by forming its paste with sand or you can do it in the form of a concrete, in which some grains of the pebbles are also used in it. So cement itself is a fine binding powder, and its paste can be formed with the water. And in construction, cement paste along with concrete and mortar both are used. So these three terminologies are interchangeable and used in structural infrastructural applications. So cement paste, whenever it is used, means that the cement powder making the paste with the water. Whenever the mortar word is used, it means that the sand is being added with the cement powder for the construction purpose. And if the concrete is used, it means that some other inclusion in the form of the particulates are also added into this mixture. So it's a binder material which is used extensively into the construction as a working material. So why cement is preferred for structural material? So there are the different reasons. Number one is the ease, shapeability. Second is the low manufacturing cost, and the third one is higher compressive strength. So all these are the different properties by which we can prefer the cement for different structural constructions. So these are some decorative items which cement basically cement is used in this structural applications. So if you're talking about a composite and heading toward the nano composites, what are some basically the loopholes that was also still there? And there was a demand of more and more advanced properties from the composite materials. Then the nano materials comes into play its role due to the high aspect ratio, high modulus, greater strength, and reduced density. All of these different properties of the nanomaterials make us suitable to add them into the composite materials to enhance their properties and form the nanocomposites. So the nanocomposites obviously refer to the nanomaterials. Whenever the nanomaterials are added into these composites, or one of the material which is added into the composite is of the nanometer range. So their high aspect ratio, their higher strength, their less density, all these are the famous properties that helps to give new and improved properties to the nanocomposites. So the materials which are extensively used as the nanomaterials are carbon nanotubes, layered materials, buckyballs. So they were the materials that were used initially as nano composites. So what is the role of these nano reinforcement into the material failure? How we can say that by adding the nanomaterials, we can get reduced, or we can get robust resistance against the material failure. So what is that property which nano reinforcement is going to impart into the composites, which can reframe them from the material failure? So obviously their higher aspect ratio and their more interaction with the matrix and the filler, or you can say matrix and the reinforcement. These are the two ingredients. Their interface play an important role. At the interface, if there is a greater strength or there is a greater bonding between the matrix and the reinforcement, then we can talk about that the strength of the material will be higher. So decrease in the defects also are expected in these nano composites due to the addition of the nano reinforcement. So decrease in defects also produces the enhanced properties of these materials. So also it does matter that the nano reinforcement which is added into the composites is in which amount. The amount of the reinforcement or the type of the reinforcement are the two major or important parameters which will be going to conclude that whether the material will be going to play its vital role against the material failure or not. So the percentage by weight of the nanoparticles which are introduced into the composites is very low due to the high aspect ratio of your nanomaterials. So how about the graphene, which is a newly introduced material in the class of the two-dimensional materials as a nano reinforcement, or how graphene can play its role as a nano reinforcement for the cement. So some brief introduction about the graphene. Graphene is the first experimental material in the class of the two-dimensional materials that was discovered in 2004 by Manchester Group, in which I have received my PhD degree under the supervision of these two scientists, and the era in which they have received the Nobel Prize, we were working upon there. So graphene was introduced or defined as in history, that was not a new material. The graphite is a very, very ancient material which were used as different applications and was studied extensively. Its structure, whenever was in literature considered, and a single layer of the graphite was whenever called, the graphene names were introduced in history. But experimentally, that was not possible to isolate it, which was done in 2004. The complete isolation or experimental isolation of that material, experimental isolation was done, which is a hexagonal structure of the carbon, covalently bonded carbons. So the different forms of the graphene which are extensively used for different applications are graphene oxide and reduced graphene oxide. Graphene oxide is taken as an insulator, and reduced graphene oxide is with change properties. Whenever you reduce the oxygen content from the graphene oxide, then you call it as a reduced graphene oxide. What are the different fabrication routes which are used extensively for this graphene fabrication? Mechanical exfoliation, which was the route which leads to the first experimental extraction of the graphene, was that particular route. Then chemical exfoliation, chemical synthesis, and epitaxial growth, CVD, are different famous routes which are used for graphene fabrications. So here we will be talking about graphene oxide, which can be very well extracted from the chemical route. So the chemical synthesis route for graphene oxide are more than one, but which is easily used into the lab scale.
Dr. Prasad,
yes.
Can you sum up your presentation?
Okay.
Can you sum up? Yes.
Okay.
Thank you.
So, so we'll move toward the fabrication of the graphene and reduced graphene. So the synthesis of the reduced graphene was with the help of the hydrothermal method. So in this work, hydrothermal method was used for the synthesis of graphene oxide. So the different steps for this was used are represented into the schematic diagram. And then that reduced graphene oxide was used as a reinforcement for cement. So the process used for the cement and RGO fabrication was that wet method, so in which the mixing of that powder along with RGO and some curing was done. So curing is the same process in which usually the cement is let to stay and sprayed or sprinkled with water to settle down to reduce the loss of the moisture from the cement. So previous literature survey tells us that RGO is very well used as a nano reinforcement for the for the basically additional properties added to the material structure. So different ratios can be added for of RGU for the cement nanocomposites. So this is a schematic diagram with the help of which the improved hammer method was used to produce the graphene oxide, and then that graphene oxide was reduced by using the autoclave, and then it was mixed into the cement to produce these cement blocks, cubical cement blocks. One of the cement block was without, which is called as the controlled block, was without the inclusion of the nano reinforcement of reduced graphene oxide, and other was with 3 ratios of the RGOs. So the different results of the which were used up over there, characterization techniques for the inclusion of the nano reinforcement into this cement was FTR, XRD, SEM, and then some testing mechanism of UTM was done. So the FTR of the GEO predicts the famous peaks with the oxygen groups are present into this. So the graphene made up over there contain these characteristic peaks. XRD analysis also shows the 001 plane, which is coming from the graphene oxide. So this was a SEM micrograph of the fabricated graphene oxide, which is in the form of the stone-like flaky structure that was thick flakes represents the unexfoliated part, and the lighter ones are representing the more exfoliated regions. So that reduced graphene oxide was also tested against the FTR and represents that these peaks are reduced, all of these peaks which are present in GEO are reduced in their strength. And then that is the FTR spectra of the ordinary Portland cement, which was used for this purpose, representing all the silicates, sulfates, and some water peaks. That was the characteristic spectra of ordinary Portland used for this purpose. Now, this represents the inclusion FTR spectra of all the samples which were used with the different ratios of the RGO. So summing up all these peaks represents that there is a proper inclusion of reduced graphene oxide into the cement. So the peaks of the cement and the peaks of the reduced graphene oxide were present into this spectra, representing the successful inclusion of the different percentages of
the Sam.
Yes.
Our next speaker is waiting. So please sum up because we are run short of time. Yes.
So move toward the testing analysis, compressive testing analysis of these samples. So the compressive testing machine used for this purpose was of 10 tons, and the facility was used by the civil department of the UT Lahore. So whenever the cement blocks were placed up over there, certain buckling load, fracture or failure load was obtained, which represents that the controlled sample has a 62 kilonewton load, which enhanced with RGO to 65, 1% of RGO to 65%. Then the enhanced percentage of the RGO increases that failure load, and the more increased percentage of the RGO increased the failure load to 78 kilonewton. So the strength corresponding to these failure load was also calculated by the machine, and also representing that the inclusion of the different percentages or the higher percentages of the RGO has increased that compressive strength. So the theoretical analysis of that buckling was also done, or critical buckling load was also done with the help of the Euler buckling theorem, which represents that they are well in contact with the experimental analysis. So the Euler buckling load calculated was in newtons, and that PCR value shows that controlled sample has a load of 2459 Newton that has enhanced with the inclusion of RGO to 3105 Newton, and that was percentage increment was 20%. So it was obtained that in comparison with the control sample, 20% enhancement into the critical buckling load was obtained theoretically, which was in agreement with the experimental one. So they were more or less close to one another. So around 26% for theoretically it was obtained, and around 23% was the machine testing analysis. So the summary of this says that the RGO is one of the nano reinforcement that can be added into the different percentages to get the reinforcement of the cement, and can also be very effective against the buckling phenomena, to control the buckling phenomena. So thank you so much. That is the end of this.
Okay, thank you so much, Dr. Ittasam, for impressive and novel work. We are already run short of time, so we will move to next speaker, Ms. Lauren Miller, currently working as research postgraduate in the Department of Electronics and Engineering, Durham University, UK. Over to you. Her title talk will be Development of Electronic Nose for Chemical Detection. Over to you, Ms. Lauren.
Good morning, all. I'm just trying to share my screen. I think
Yes,
the previous
please.
speaker is still screen sharing.
Dr. Ittasam. Hello, Dr. Ittasam, are you there? Please stop sharing.
Thank
Yes,
you.
Lord. Yes, it's shared.
Wonderful. Can you see those slides?
Yes, we can see your slides.
No problem. So good morning, all, and thank you. Well, good morning, UK time. And thank you for inviting me to talk about my recent accomplishments as part of my PhD at the University of Durham, based in the UK. My research aims to develop an electronic nose for chemical detection. Within my first year of study, I have fabricated and characterized a series of bottom gate, top contact, metal oxide thin film transistors, or TFTs for short, which have successfully detected the presence of volatile organic compounds, or VOCs, specifically acetone and alcohol odors, for applications in the healthcare industry. The next slide provides an outline of my presentation. I am firstly going to introduce my research aims and explain the operation of a thin film transistor. Secondly, I will discuss my results achieved to date, which summarize the effect of increasing the number of semiconductor or active layers and annealing temperature on electrical performance. Thirdly, I will describe the detection of VOCs by single-layer tin oxide and bilayer
Application of the
tin oxide, or ZTO, thin film transistors based on my VOCs by single. Finally, I will close with conclusions and welcome questions from the floor. So over 200 types of volatile organic compounds are found in the human breath and are measured in the sub-parts per million range for a healthy individual. Abnormal concentrations of VOCs in exhaled gas from humans can be used as disease-specific biomarkers for the non-invasive and early detection of medical conditions, such as acetone for diabetes. Current technology suffers from poor selectivity and prolonged response times. Nonetheless, metal oxide thin film transistors could be used to improve the remote detection of volatile organic compounds, as they provide unmatched sensitivity through current modulation by the gate electrode. A substrate consisting of 5 thin film transistors with variable channel length is shown in Figure 1. The key advantages of my work include using solution processed materials, which are highly abundant. The fabrication method involves spin coating and annealing, which is simple, versatile, and thin film transistors can be manufactured in just a few hours. The operating range of the thin film transistors presented in the following slides is from -40 to 40 volts, as they are based on silicon nitride or silicon oxide as the dielectric. Therefore, I also aim to incorporate high K dielectrics such as zirconium oxide to ensure low voltage operation in the long term. I fabricated the transistors shown in Figure 2 to build on works from within my group on single layer ZTO TFTs, which I will detail shortly. A thin film transistor is a 3-terminal device consisting of a grounded source, drain, and gate. In this case, the highly doped silicon wafer shown in orange acted as the gate. The first layer of ZTO was spin coated and annealed at 350 degrees Celsius. And after 1 hour, the second layer was deposited and annealed at 400 degrees Celsius. Aluminium source and drain electrodes were then deposited on top of the semiconductor via thermal evaporation. And this is why we call it a bottom gate top contact configuration. At 0 gate voltage, no charge accumulation occurs at the semiconductor dielectric interface, so the device is turned off. For an N-type device such as this one, an applied drain voltage polarizes the dielectric silicon nitride, which causes the accumulation of electrons at the interface, and the device turns on. The results show a working transistor, and I was able to extract key parameters such as mobility, on-off ratio, and threshold voltage from the transfer characteristics shown in Figure 4. These transfer characteristics are obtained in the saturation regime, as a constant drain voltage of 40 volts is maintained while the gate is swept. The output characteristics shown in Figure 3 indicate clear, linear, and saturation regimes, excellent switching ability, and low leakage current, as the device sharply turns on under an applied positive gate bias. Conversely to Figure 4, these output characteristics are obtained by sweeping across the drain and maintaining a constant gate voltage for each curve. The threshold or turn-on voltage is approximately 0 volts, which is required to enable the device to operate as a battery-driven and handheld sensor. Furthermore, chemiresistor sensors based on metal oxides found in commercial appliances, such as smoke detectors for carbon monoxide detection, operate at 0 applied gate bias. Therefore, a turn-on near 0 volts is advantageous to compare sensing performance accordingly. This slide summarizes the work conducted by my group on single-layer ZTO thin film transistors. The effect of increasing the number of active layers and annealing temperature on electrical performance is demonstrated. In Figure 5, 300-400 denotes that the first layer was annealed at 300 degrees Celsius, and the second layer was annealed at 400 degrees Celsius. You can see that threshold voltage or turn-on voltage is dramatically reduced, and mobility is increased after both layers are annealed at higher temperatures. This may have been owing to a greater proportion of metal oxide metal bonds, which created a highly ordered lattice and therefore greater crystallinity to facilitate charge transport. The performance of single-layer and bilayer ZTO thin film transistors with all layers annealed at 500 degrees Celsius is shown in Figure 6. Hysteresis is significantly reduced with the addition of a second active layer, and the electron mobility achieved is the highest reported to date for solution-processed ZTO TFTs at 9.49 centimeters squared per volt per second. Next, I chose to fabricate tin oxide thin film transistors to compare against the literature, and tin oxide is also an ideal material for oxygen-related gas sensing. Thermogravimetric analysis, or TGA, was performed to illustrate the different stages of solution processing and provide the optimum annealing temperature of the films. The TGA curves for each sol gel are plotted in Figure 8. You can see that the graph is divided into 3 sections. The weight reduction prior to 200 degrees Celsius was attributed to the evaporation of the organic solvent used, which was 2-methoxyethanol. The changes recorded from 230 degrees C to 300 degrees C represented the decomposition and separation of the chloride ligands in the precursors. No further weight loss was recorded after 450 degrees Celsius, which indicated that a dense metal oxide metal network had formed. The thin film transistor annealed at 450 degrees Celsius had increased mobility, which is consistent with the results presented previously. The thin film transistor annealed at 350 degrees Celsius could have contained a greater proportion of metal hydroxide bonds due to the incomplete dehydroxylation and condensation processes, which then acted as traps and hence hindered electron transport. The tin oxide thin film transistor annealed at 350 degrees Celsius was then able to detect acetone with respect to time. The off current of the device, or as you can see, when a negative gate bias is applied at -40 volts, the off current increased by 2 orders of magnitude following overnight exposure to acetone. And this was attributed to free electrons within the tin oxide film that were released following a redox reaction between acetone and the oxygen species adsorbed to a surface when the thin film transistor was left in ambient after fabrication. Following exposure, the device was placed on a hot plate at 100 degrees Celsius for 1 hour, and electrical performance was recovered successfully, as the transfer characteristics before exposure and after heating were well matched. Finally, bilayer thin film transistors annealed at 500 degrees Celsius were exposed to acetone and another reducing vapor, isopropanol or IPA. The second layer or open channel was varied to optimize selectivity. The 3 devices under test were therefore ZTO followed by another layer of ZTO, ZTO followed by zinc oxide, and finally ZTO followed by tin oxide thin film transistors. The change in drain current at 0 applied gate bias was computed and confirmed that the sensing mechanism was analogous, as the conductivity of the channel increased in every case following exposure. To conclude, I have successfully fabricated metal oxide thin film transistors and extracted key parameters. I have achieved the highest mobility to my knowledge for ZTO thin film transistors. I have also found that annealing films at higher temperatures and spin coating an additional active layer resulted in improved mobility and near 0 volts turn on. As a proof of concept study, tin oxide thin film transistors exhibited a highly sensitive and time-dependent response when exposed to acetone. Following on from that, heterostructure or bilayer ZTO TFTs were exposed to acetone and another reducing vapor IPA, and the results supported these initial findings. I'd like to conclude my talk there, and I hope that it was short and sweet. And thank you for listening. I'd like to extend my thanks to my group and supervisor back in Durham, Dr. Majib Chowdhury, and I'd like to welcome any questions that you may have. Thank you very much.
Thank you very much, Ms. Lauren. Any question? Okay, it was very nice and informative and beautiful talk given by you, Ms. Lauren. Thanks again.
My pleasure.
Now we will move to our next speaker, Dr. Aisha Akib, currently working at Technical University of Munich, Germany, Department of Physics, Chair of Experimental Physics of Functional Spin System. Her field of interest are solid-state physics, condensed matter physics, and material sciences. She has 35 publications in reputed journals with the citations of 586. Today, she will give talk on novel magnetic materials, hosting skyrmions for spintronics. Over to you, Dr. Aisha.
Thank you very much for very kind invite and very kind introduction. Can you hear me?
Yes, we can hear you.
Okay. I will share my screen.
Yes, please. Please share.
Can you see the presentation mode?
Yes, we can see.
Okay.
Continue. Yes.
Hello, everyone. So, as we are here to talk about materials, I would like to introduce you about some special magnetic materials which host some special textures. I am from Technical University of Munich, and I would like to show you a little bit from where I am. So here in Germany, it's from Bavaria. So Bayerisch is very famous for BMW. So Bayerisch motor wears. And there are something special about Munich is that we have a lot of institutes together, Max Planck, LMU, as well as some Walter Meissner Institute, and one university is Technical University of Munich, where I belong. So before starting, I already want to thank people who have contributed to this work. The slide is very crowded. I would walk you through. So especially I would like to thank Professor Maxime Mostovoy and Professor Thomas Palstra from University of Netherlands, University of Groningen, Netherlands, and Maria Azhar from University of Karlsruhe for theoretical support, and all other people, our group members. And I would like to thank MCQST, which is Munich funding, which have funded a small group of me at this university recently. And I would like to thank my group members. Today in this talk, I would like to tell you about a special magnetic material. And then I would want to introduce you how we can find different properties of this material by a simple magnetoresistive method. And I will summarize. I'm an experimentalist, so my talk will be mostly about experiments. Now, what are chiral magnets? So my talk is really about a specific magnetic material, and the difference, if you compare all other magnets you use in daily life, there is a difference of symmetry. Most of the materials, most of the magnets are centrosymmetric, meaning if you apply inversion, there is no change. Their crystal structure stays the same after inversion or before inversion. They are totally the same. However, there are only few magnetic systems which acts as which have crystal structure just like our hands. If we put inversion on our hand, either it's left-handed or right-handed, they cannot be superimposed. They are not identical. In the same way, there are crystals where you can see these magnetic atoms. Here in this crystal, manganese silicite, magnetic atom is only manganese. And this manganese is placed on places in such a way that if you apply inversion operation like this and move one atom from XYZ place to -X, -Y, -Z place, they cannot be the same. You cannot superimpose. They are either left-handed or they are either right-handed. And this distribution of atoms within the system really triggers their special properties. And this is what is all about chiral magnets. So chiral magnets are simply magnets where magnetic atoms are distributed like our hands. They have certain chirality. So normally magnets, you can think that each magnet has different atoms and each atom carries a spin. And these spins, if you apply certain magnetic field, they all align. They are nice, aligned. These are normal magnetic material. Famous example is yttrium iron garnet. However, there is an exchange interaction, which is their Jalushinsky-Moria interaction. It's mostly zero for magnetic systems, but in this system, which I am talking about, it's non-zero. So it tries to align spins perpendicular to each other. Obviously, it cannot align perpendicular. It's a very small contribution, but it will tilt your magnetic structure away. And this is what we are interested in. We are interested in twisted magnetic structures. And if you look at the phase diagram, this phase diagram is usually not shown for normal magnetic materials because there is only ferromagnetic phase and the paramagnetic phases. But if you look here, there is a very colored phase diagram. And here, if I tell you at large magnetic field below Curie temperature, here above 1, everything aligns along the applied field direction and everything is field polarized, just like normal magnets. There is no difference, nothing special. But as you reduce the applied magnetic field, they start to twist away from the magnetic field. And here in this fermion lattice small pocket, the red one, you get very twisted structure like this round shape orientation of magnetic moments, and they are very special. And I will tell you now why they are special. If you look this girl with this hair, you can think that the straight hairs are just like field polarized. So everything is straight, and then there are curly hair. But if you take a straightener, you can gradually make everything straight. There is not a lot of effort. But if you look here, this hair, there is a knot in the hair. And if you try straightener, whatever you do, this knot will not go away very easily. The same is holds here. So the fermions theoretically is has an energy minimum, and you cannot go from field polarized to from fermion state to a field polarized state very easily. And that's why it makes them very special, and that's why they are very famous. They has a lot of similarities with domain walls, but they are robust. They are topologically protected, meaning the topology of this is much different from this. Now, coming from the phase diagram, all these materials, they are very small family, which has such structure that magnetic atoms are distributed differently. And they all share this generic phase diagram. I am working on copper oxyselenate. Here, magnetic atom is only copper and is distributed in some specific places. And this is a magnetic insulator and has very low magnetic damping. We grow these crystals, and these crystals are very high quality. In terms of damping, it has 10⁻⁴ damping. And damping simply means if you send some information inside a spin wave, it can travel very long distance before it will be diminished. Now, I would like to introduce how we can detect this method, these different types of magnetic structures by a magnetoresistive method. Magnetoresistance is a typical name used whenever a resistance of a material changes with an applied field. Then we call it a magnetoresistive. And spin Hall magnetoresistance is a little bit unique. So what we do, we polish this crystal and we put a very thin platinum metal. Platinum is very special. It's a very heavy metal and carries very strong spin orbit coupling. There is a spin Hall effect, which is different from ordinary Hall effect. So ordinary Hall effect, you apply a perpendicular magnetic field, you create some deflection of electrons, and then you will have some Hall voltage. However, in spin Hall effect, when you don't need applied magnetic field, if it's a heavy metal, spin up electron will deflect one direction and spin down electron will deflect on the other direction. this has a lot consequence. So what happens is you are sending a current from normal metal, and it will spin up will go here, and spin down will go here, and you will create some accumulation. And this accumulation can talk to your magnet. Although the magnet is magnetic insulator, there is no current which can go inside, but only the spin can talk to the magnetization of the magnet. When the spin is parallel to the magnet, which is flowing into the normal metal, when it's perpendicular, it can exert a torque, which is called spin transfer torque. The resistance will be large, and when it's parallel, it will be reflected back, and it will be small resistance. So this is basic principle of the spin Hall magnetoresistance. With this, we actually just measure the resistance of the platinum metal, and we can tell underneath magnetization direction. You expect to have the resistance of the platinum will have sinusoidal dependence. Where it's perpendicular, the resistance will be large. Where it's parallel, the resistance will be small. Now, the unique thing is that our magnetization, it doesn't align parallel to the magnetic field all the time. It has a texture. So you expect to have changes in this periodicity. And to just, there is a lot of mathematics, but the idea is very simple. So the idea is that whenever the electron spin in platinum will be parallel, it will be small resistance, and when it's perpendicular, it's high resistance, and you can tell if there is a texture or not. So if we measure such resistances, we can get amplitude here and a phase by fitting these curves, and we can plot them in a color plot. Here, each color is a data point from these such measurements. And you can see the phase is varying from 0 to 120 degrees. And here is magnetic field, and here is temperature. What it tells you is that at large magnetic field, the angle between the magnetic field and the magnetization is 0, meaning everything is aligned with the field. And as you go down, the angle between the magnetic field and magnetization start to increase, and you go to the yellow phase. So with this, I just wanted to emphasize that you can, with this simple technique of magnetoresistance, you can detect such complicated textures, and it's not valid only to skyrmions or very complicated things. It's also valid to all other magnetic insulators. With this, I think I'm already running out of time. I would walk you through the conclusion. So we have a very different magnetic system, which resembles in many cases to normal magnetic systems. And there are some differences, but with a simple magnetoresistance technique, we can detect its properties. And there is a theory about it, which is actually summarized in this paper. If you are interested, you can also ask me about it. With this, thank you very much.
Thank you very much, Dr. Aisha Keep. It was very informative and impressive talk. We learned a lot from you. Thank you very much. With this talk, we have successfully completed our first day of international webinar on the material sciences in current era by the grace of Allah Almighty. Thanks a lot for all worthy speakers from Pakistan and from all over the world. We will meet tomorrow morning, inshallah, for the next successful second day of webinar. Till then, take care and Allah Hafiz.